The role of a dispersant is to adsorb onto the pigment surface, prevent flocculation of the pigment particle during milling, resulting in a stable pigment dispersion. Dispersants provide several key benefits during both formulation and final appearance, such as reducing milling time and viscosity, improving appearance, and enhancing final coating properties. A dispersant consists of two parts: an anchoring segment that adsorbs onto the pigment, and a polymeric chain that creates a steric barrier that stabilizes the dispersant. Lubrizol's Solsperse polymeric dispersants, also known as hyperdispersants, are polymeric materials designed to offer significantly higher levels of performance. They are typically higher molecular weight, and this means they may contain multiple anchoring groups and stabilization chains. They can be tailored to work across a broader range of pigments or fillers and in different media. Due to their unique structure, polymeric dispersants can provide specific benefits to formulators and end product manufacturers: higher quality, improved flexibility, increased productivity. There are multiple methods to stabilize a pigment in a medium, but electrostatic and steric are the two main types. Electrostatic stabilization, also known as charge stabilization, uses electromagnetic forces to achieve particle separation. It is effective only in high-polarity systems like water. Steric stabilization, which physically separates the particles, was originally designed for use in low to medium polarity systems, but its use has been extended for all polarities. The dominant mechanism for stabilization with Solsperse hyperdispersants is steric. Dispersants are two-component structures. The anchoring group provides strong adsorption onto the pigment surface. Polymeric chains, which are attached to the anchor group, provide the stabilization. It is the particular combination of the anchoring group and polymeric chains which leads to the effectiveness of hyperdispersants. Single anchor, single chain structures are polymers with terminal function groups. They are fast wetting and good with grind resins. Single anchor dispersants, by their nature, only contain one type of anchoring group. Therefore, they are most effective on a single class of pigments. Multi-anchor or multi-chain structures, also known as comb copolymers, are better for long-term stability and broad pigment compatibility. This is due to the fact that they can contain multiple types of anchor technology to work across a broad range of pigments. When choosing the right dispersant, there are several key factors to consider. A dispersion typically consists of pigments or fillers, solvents, resins, and dispersant. The first factor in choosing the right dispersant is the type of particle being dispersed: organic, carbon black, inorganic, or fillers. Each one has a different surface chemistry and structure. The dispersant needs to anchor strongly onto the pigment or filler, and different pigments can have very different surface chemistry. Inorganic pigments and fillers disperse best with acidic or anionic anchor groups. Organic pigments and carbon black disperse best with basic or cationic anchor groups. This is represented by the outer part of the wheel. The second factor to consider is the system. The dispersant must be soluble and compatible with the solvent and resin system to get a good, stable dispersion. This is represented by each section of the wheel. The third factor which influences dispersant choice are the application and processing conditions. With some difficult to stabilize organic and carbon black pigments, the use of a Solsperse synergist can enhance the performance of the polymeric dispersant. This is represented by the outer ring. Lubrizol maintains a portfolio of hyperdispersants for a wide range of solvents and pigment types. Implementing these steps will result in a low viscosity, high color strength, stable dispersion. After choosing the preferred dispersant, the optimum amount of hyperdispersant required is dependent on the surface area of the pigment. If too little is used, the full benefits will not be realized. If too much is used, the thickness of the protective barrier is reduced as a result of overcrowding on the pigment surface. Performance properties are optimized at the correct dosage. Viscosity and particle size are at a minimum, and appearance properties are maximized. Through experimentation, it has generally been established that the theoretical dosage level of a hyperdispersant in a pigment dispersion equates to 2 mg of dispersant per square meter of pigment surface area. This can be expressed as percent agent on the weight of pigment, or percent AOWP. Percent AOWP equal BET surface area meters squared per gram divided by 5. Implementing these steps will result in a low viscosity, high color strength, stable dispersion.